my hot take on that, and I'll be happy to be proven wrong, but I think there is not a single humanoid robot today that actually generates value. Meaning, there might be a robot that does something fairly close to what it's supposed to do in a factory or in a warehouse, but it's not the exact task. So in the end, it's not generating value because it's not doing the actual thing it's supposed to do.
All right, everyone. Welcome to another episode of the TWIML AI podcast. I am your host, Sam Charrington. Today, I'm joined by Nikita Rudin. Nikita is co-founder and CEO of Flexion Robotics. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Nikita, welcome to the podcast.
Thank you. Very excited to be here.
I'm excited to have you on the show, and I'm looking forward to digging into our topic for the conversation, which is really digging into the gap between, where we are today with robotics and where we need to be to fulfill the vision of the technology. You've been working in this space for quite a while. You did your PhD at ETH Zurich and spent some time at NVIDIA. Why don't you share a little bit about your PhD and the focus of your research?
So when I started, we were trying to use simulation with reinforcement learning to teach a legged robots very simple things, like just walking on flat ground. And when the robot could take a few steps, that was already a big success. And the core focus was to reduce the training time needed to achieve that.
And
So
when you
we
say
went
legged, like a quadruped?
like a quadruped, a big legged robot dog. We were not using bus dynamic spots. We were using Anybotics Animal. Anybotics is a Swiss startup that was a spin-off from our lab. It's very similar to a spot, but it's red and made in Switzerland. Yeah, we were really trying to reduce the training time needed to achieve that. So before I started, there were some results of reinforcement learning for such quadrupeds, but it would take weeks of computation to achieve anything. And using GPUs and massively parallel simulators, we managed to reduce that to just a few minutes. So actually, we had a demo on stage at some point at some conference where we were running training live on a laptop while I was holding the robot. And every 15 seconds, the laptop would send the latest policy to the robot. And you could literally see how it went from just falling over to taking a first step. And then after 3 or 4 minutes, it would be able to walk around the stage. And that was a pretty cool visual demo for everyone to see exactly how the learning process happens. And from there, my PhD was pushing the agility of that robot using the similar techniques. It was still training neural networks in simulation and then transferring them to the real world. But the inputs got more complicated, the tasks got more complicated. So by the end, we could go to a search and rescue facility here in Switzerland. So you have to imagine collapsed buildings, a lot of mud, moss, gravel, big rocks, terrain that is very hard to navigate even for a human. And we would just tell the robot to go from point A to point B, and would use its whole body. So it would use the knees to climb on top of big rocks and then jump over gaps. And all autonomously, all end to end, using images and the state of the robot to plan its next actions.
In telling that story about, deploying this robot in a search and rescue context, envisioning the demo, I've seen similar things. The robot dog is going, maybe opening some doors. Maybe that wasn't part of your demo, but I've seen similar demos of, the robot dog like climbing hills and crossing rubble. And I think those demos, you know, attempt in many cases to land the idea that, hey, like flag in the ground, we're done here. Like, talk a little bit about the distance between, what you were able to accomplish with that demo and like what you think needs to be done to deploy one of these robot dogs in a real search and rescue scenario, for example.
It's a great question, and I had this debate so many times, even with my colleagues at NVIDIA and ETH. The general question is locomotion solved or not? And we already had this debate 5 years ago when the robot could just barely walk on flat ground, and people were saying, "Yeah, locomotion is solved. We don't need to focus on it anymore." My take was always like, "No, until the robot can really go anywhere a human can go, and you don't even need to think about can it do it or not, how reliable it is." My take is that locomotion is not solved. Um, so where we are today is that anything that is blind can be very very robust. Blind meaning that the robot does not perceive its terrain, so it's just reacting. That makes the training much easier because you just have to throw a lot of things at it. It always tries to be stable. Especially for a quadruped, it's fairly easy to remain stable. And for example, it can even walk upstairs. It will just hit the first step, realize there is something, and then climb up. Doing it with perception. So now you want it to actually react. You don't want it to hit the first step. You want it to place the feet much more carefully. That's harder. Today, in end of 2025, we're at a stage where we can do that. We can have fairly good policies that plan the sequence of actions based on the perceptive inputs. Because we're training everything in simulation, this means that we need to be much more careful in how we simulate those sensors as well. We need to put a lot of effort into creating complicated terrains that can be seen by the cameras, and also all sorts of noise models to simulate all the, the disturbances and defects of those images.
So what I'm hearing you say is that the addition of the additional information that you would think would help actually makes it more difficult because it introduces a lot of noise. And whereas previously the robot could kind of stumble through the terrain, now it's trying to incorporate this visual input to plan, but it ends up, making it, what actually happens when it is trying to do this? Do you see it stuttering, or does it just not work? Is it just hard to train from a model perspective? Like what happens?
So, I mean, in the end, what happens is that the final behavior is better if you do everything right. But that's a big if. um, the typical thing we refer to is the so-called sim to real gap. If you're training things in simulation and deploy them in real life, it's not the same. And things that work really well in simulation might not work at all in real life. That sim to real gap is much larger once you have perception in the loop. Once you're simulating either depth images or RGB images, it's even worse. So that makes the job of the researcher, of the engineer harder. You need to cross that sim to real gap for both the physics of the robot and the perceptive inputs. You have to simulate the sensors carefully. But if you do it right, then the final behavior is actually much better because you can see that the robot is not simply reacting to whatever is happening under its feet, but actually planning accordingly in advance.
Is this problem of locomotion solved then with with vision? At least for let's take quadrupeds as an example, or are there still kind of outstanding issues? Like, is there a generality gap, or how do you think about it?
It's interesting. So it really depends where you draw the line on locomotion. So once the robot can cross complicated terrain, the next step goes more into navigation, which means where should it go? Should it climb that thing, or should it avoid it? For now, everything I've described so far was mostly using geometry, so there are no semantics. But now, if you imagine the robot
Meaning
walking
you give
behind
it
me,
a point A and a point B, and it's going to take the straight line and like kind of plow through whatever is between here and there, as opposed to think about which way to go.
more or less, if there is a huge wall, it might avoid it, but then
Okay.
mostly it will try to climb on whatever is in front of it.
Okay.
Now, if you imagine a robot walking behind me in the office, you don't really want it to climb on every single desk. You want to avoid some things, but also walk on others, right? So if there's stairs, you want to take the stairs, but you don't want to hit plants or whatever else. Which means that suddenly you have to add semantics to the policy.
And what does it mean to add semantics to the policy?
Once again, if you go from simulation to reality, it makes the sim to real gap bigger because suddenly you have to simulate all these offices, all these different objects. Plus, you probably need to give it um, images, not just depth images. You need to give it RGB images, which means you need to simulate it in a photoreal way. Or the other option, which is probably the more correct one in the short term, is to split the problem. So you train the robot to be very good at walking on anything, but you don't give it semantic information, and you train another thing on top, which will be you can call it the planner or a higher level policy that will steer it around.
And now, yeah, historically in the conversations I've had with roboticists, like this has been a big debate, whether, we should be using end to end deep learning models that can figure all this stuff out, or using a more modular approach. It sounds like what you're saying is that a more modular approach can still be a pragmatic way to overcome the challenges of end-to-end training.
Yes, it's interesting because my whole PhD was about going more and more end to end for specifically for locomotion. And still I'm here arguing that we should not do everything end to end. I think at some point we'll get there, but in the short medium term, as you said, the more pragmatic approach is to split the problem and use different techniques for different parts of the problem.
We're splitting the problem into kind of a locomotion model and a planner model. Does the planner like what's the objective for the planner when you're trying to, the English language objective is I want this thing to intelligently choose the best path. But what is best path? How do you define that? How do you create an objective around that? Is it the path that maybe it's the path that uses that's most power efficient if you're in a robot, or maybe it's the path that, gets you there faster or least distance? Like how do you balance all that?
There are different ways to do this. If you still choose the RL route, when we're doing that, you can train these planners with reinforcement learning. And typically you have to define this reward function. It would include things like don't hit anything, so avoid objects, don't move too fast, because that's one thing that makes robots seem very dangerous. These reinforcement learning policies will try to optimize everything, so they will go very, very quickly to the goal. This is not really what you want with a robot that operates around humans. So typically, we're actually trying to slow them down as much as possible. Um, yeah, that's mostly it. And then it depends really on what is in front of the robot. Like, there might be things that it's okay to walk on, others that it's not. There is also another approach. Once you split the problem in half, you could train the locomotion with pure reinforcement learning and simulation, but you could train the planner with other data. For example, videos of humans walking around the office, and you can extract the trajectories from that. And then you don't really need reinforcement learning anymore. You train behavior cloning, imitation learning policy that will just steer the robot just like a human would walk.
And thus far, speaking about how a human would walk, thus far we've been talking primarily about quadrupeds. How much of all of this translates from quadruped to humanoid robots?
All of it transfers. That is the magic of reinforcement learning. That these policies don't really care if they're controlling a quadruped or a humanoid. And this was the big switch from my PhD to Flexion, where we're working mostly on humanoids, and we've seen that the exact same techniques transfer. There is one interesting thing that happens with humanoids.
That makes sense to me for a planner, but it's less intuitive for a locomotion model. And maybe I'm thinking of a locomotion model that maybe the locomotion model itself that I'm thinking of is like split into multiple components, but um, let me be more specific. I'm including in locomotion like, the outputs that control stepper motors and all that kind of stuff. Is that part of what is trained in the locomotion model? And then I would think that you would need to at least like tune it or do something else to if you're going to change the form factor of your robot.
Mhm. No, this is a very good point. When I say it transfers, the general techniques transfer. The models themselves don't. So for sure you need to retrain a new policy, a new controller for the new robot. But if your all the simulation pipelines are general enough, it can be as easy as changing the input file, the URDF that describes the robot, retraining it, then you're ready to deploy. The tuning part is an interesting one because it is a little bit harder for humanoids compared to quadrupeds. And I don't think it's really related to the fact that it has 2 or 4 legs or anything like that. Personally, I think it's mostly related to the fact that we have very specific expectations of how a humanoid robot should walk. Whereas a quadruped will, if it walks slightly differently from a dog, it's completely fine. But a humanoid, if it doesn't move the arms in the right way, if it bends the knees too much or walks a little bit sideways, humans have a very strong reaction to that.
I saw a tweet kind of touching on the same idea just the other day, and it was essentially this humanoid robot that was kind of locomoting like a quadruped, like it was like on its back with its arms like this and like moving really quickly. Um, and the main thrust of the tweet was that, humanoid robots move like humanoid robots because we like that's our expectation, but that, there are potentially other, even with that form factor, there are potentially other more efficient ways for these things to move, but they just seem wrong to us.
Yeah, that's true. But if we want these robots operating around humans, we have to create some trust. So we have to take the less optimal route if it makes humans feel a bit more comfortable.
We've been working on robots for a really long time, but it seems like over the past year, like we're, seeing advancements of and via video demos coming very quickly. Like, yeah, I kind of asked this question before, but I want to like have you kind of parse through how to think about, these videos. Like, you know, we were seeing humanoid robots walking at the beginning of the year, and now they're running. Now they're doing dishes and all these things. Like, what goes into creating a demo like that? And what are the limitations of what it says about what the robot is capable of?
First, I want to say that it's really exciting that the whole ecosystem is moving so quickly. Feels like every single day there is a new video of a new robot doing something, and that's really really good. We see a lot of progress both in hardware, but also how it's on the AI side as well. How what these robots are capable of doing. Having said that, typically when I personally see a demo of a robot doing something, my approach is to think about what is the absolute easiest way to achieve that, and that is typically how it's done. So we are showing we as an ecosystem, we're showing a vision of what robots should be doing, but the behind the scenes is sometimes a little bit different. So, for example, if you have a robot standing and doing some sort of manipulation on a table, folding sheets or something like that, typically one of two things is true. Either there is someone hiding behind the robot behind a curtain somewhere in another room, teleoperating the robot, so it's not really autonomous. That's, let's say, one third of the cases, and the other two thirds are where the robot is actually autonomous. But to get there, 100 people had to teleoperate 100 robots to collect a lot of data, hours and hours, of, in some cases thousands of hours of robots doing very very similar things in probably the same environment. Then collect data, train a policy that can imitate that data, and then they're able to deploy robots autonomously, which is not exactly what you would see when you watch that video, because it feels like the robot can just adapt to anything and come to your home and do everything you're doing. On that front, we're just not there yet, but we'll get there soon.
Remind me the name of the company that started taking pre-orders for a humanoid robot that is, you know, ready for the home, quote
They're
unquote.
referring to 1X.
1X. I looked at that and I've had a lot of conversations along these lines about kind of where robots are um and looking at that, I question like, okay, are we like really a lot further than I think we are, or is something else happening here, and this is um, the early buyers are going to be beta testers, and it may or may not work once it gets to the house. Do you have any takes on not that specific company necessarily, but like the readiness of humanoid robots for the home?
Also, 1X is not the only one. There are a few more who announced similar things. I mean, in a way, it's good. It's very, very ambitious to sell robots next year into people's homes. I think they have a big challenge ahead of them. So let's see how far they can get next year. But usually these companies are also fairly honest that it is a beta of a beta, an alpha program. It will be just for early adopters. It will take a few more years before you can really buy these robots and send them into homes. That's partially why, as a company, we're focusing more on industrial use cases. There are a lot of other challenges with industrial use cases because now suddenly performance is really important. You need to be very fast. You cannot slow everything down, at least in most cases. Um, but it's you have a little bit more control over what's happening. So, for example, if we want to deploy 10 robots in a new warehouse, it's easier for us to send an engineer for 1 or 2 days to check that everything is in order, as they operate as they should. If they don't, fine tune a few things, and then let robots work, which is not something you can do in everyone's home.
And are the tasks in the industrial setting, I'm imagining they're more repetitive, more consistent, less variation than, run to the fridge and grab me a Coke.
Yeah, that's right. And we get to decide which tasks we tackle and which ones we leave for the future. So we can start with simpler things. A lot of it is moving objects around, bringing objects from point A to point B, moving boxes, opening boxes, taking items out, or putting objects into boxes, putting the box in a truck, sending it further. And this seems really within reach. Or next year, maybe the year after that.
But even though you might have seen a video of a robot doing that, that doesn't mean that it's, ready now and people are doing it now without, with it not being in a development phase. Is that fair?
Yeah, that's fair. My hot take on that, and I'll be happy to be proven wrong, but I think there is not a single humanoid robot today that actually generates value. Meaning, there might be a robot that does something fairly close to what it's supposed to do in a factory or in a warehouse, but it's not the exact task. So in the end, it's not generating value because it's not doing the actual thing it's supposed to do.
Meaning it's doing some variant of the thing, or it's like there's a handler that's fixing up, cleaning up after the robot as it makes a mess across the.
Exactly. Yeah. And typically, you would have more handlers than you had people before. So you could argue the value is negative. But once again, we'll fix that.
We talked about like how you create these demos and the idea that there's either real-time teleoperation or, many people doing teleoperation to collect training data. Talk a little bit about then, after that training data is collected via teleoperation, like what the approach is for training. Is that data then used as part of RL, or is that more a supervised learning type of an approach?
Typically, it's supervised. So you record the data is images of the camera and how the commands that the teleoperator sent to the robot, which typically is like how should you move your hands in space and how should you move your fingers. So that is recorded, and then a big transformer is trained to produce the same actions from the same pictures, the same images. Now, what's interesting is the whole field shifted a little bit from just training these transformers from scratch to using vision and language encoders that were pre-trained on internet scale data.
Like VLMs, off the shelf VLMs?
Typically, you take a VLM, you remove the output, and you train a new part of the network on top, and then you call that a VLA. So it's a vision language action model, where the vision language part was pre-trained before, and the action part is trained from scratch.
Got it. Got it. So as opposed to predicting next language token, you're now predicting an action token, which is then translated into, you know, a stepper motor motion or something like that.
Yeah, exactly.
Kind of compare and contrast that approach with what folks were doing before. Are we doing that because it's cool, or are we doing that because um, how much does having a pre-trained model to start with like save us from um, the generic transformers?
It's a very good question. The general thought is that it helps with generalization. But since the language and vision encoders were trained on internet scale data, um, they're supposed to generalize. A typical case was that if you don't do that, you would, you know, train a robot during the day, then you turn like if the lights go down at night, it won't be able to perform anymore. Even though there's still lights, right? Everything should just work. A human wouldn't even see the difference, but because the image embedding changes a bit, the policy doesn't perform anymore. I believe that this gets better with the pre-trained encoders. To be completely honest, this is overall the generalization capabilities are still need to be proven. I think Ross Tedrick had an amazing talk at Stanford where we were talking about their efforts at Toyota Research Institute, where they were comparing training policies on a very specific task with little data versus training more generalist with a lot of data. And they were seeing some signs of generalization, but I don't want to quote him directly, but it seemed like it's not fully understood yet how much of that generalization is coming from that.
Now map those two little data, lots of data to the transformer VLM discussion. The VLM would be the little data and the transformer was a lot of data because like we're assuming um the VLM was pre-trained or is it or was it reversed?
No, so it's actually reverse. If you include the pre-training as data that you get for free, then that you have a massive amount of data for pre-training, and then you can add less data for fine-tuning this action head.
I guess doesn't matter which one is which because the results were somewhat inconclusive is what I'm hearing.
We need to go in more detail, and I'm quoting other people here, so it's a bit hard to say. I think it makes a lot of sense to have pre-trained vision encoders and language encoders because you don't want to relearn language every single time you want the robot to do something. Like language is language. And by the way, we have amazing VLMs now, so might as well use them. There's more of a question of this action head. Should you train it on a lot of random data or just on the thing that you want the robot to do in the end? And this is still an open question.
One question that raises for me is I just had a conversation where we were talking about how with VLMs generally, they kind of ignore a lot of the visual information and really rely more heavily on the language information. And it seems like in a robotics scenario that, um, that would be even more harmful to what you're trying to accomplish. Do you run into that as a challenge?
I've heard the same thing. I haven't seen it in the VLA case. I I would guess it's because the robot cannot ignore the visual input. It's the the main source of information. What tends to happen, however, is that they ignore the language inputs. If you train the robot to always do the same thing, I don't know, if you have a box and you have an object inside, it always has to take it out. It will completely ignore the language. It will just do the same thing. It will try to guess from the image what it's supposed to do.
You mentioned the sim to real gap. Um, we've been making, this has been a known issue for, many years. We have been making good progress on closing that gap. Talk a little bit about, your experience, what is required today to create a model in sim and have it run in real. Are you doing things kind of explicitly or specifically to address kind of real world or is it just the models are better, the process is better and you don't really think about that anymore and it just kind of works?
You need to do a lot of things very explicitly. The challenge is that to cross the sim to real gap, you need to have a very deep understanding of both worlds, of the simulation and how it works, and of the real world, which means that if you want to have a robot that walks around as it should in sim, you need to go very deep. You need to know exactly what's happening between a command that the policy outputs and then all the way down to torque in the motors. And there are typically 10 different layers of transformations, even just on software, of how we go from a high level command to actual current in the motor. And it's very tempting to ignore that. But by understanding every single layer and knowing all the different transformations, then you can properly simulate it. And this really unlocks better performance.
So that suggests like the level of simulation that you're doing isn't like, you pull up your sim environment and get generic humanoid robot, and you're going to train some model and deploy it to something else. It's like you have a digital twin of your humanoid robot in a simulate like a high fidelity simulation environment, and you're training, to a very fine level of detail, which sounds very computationally expensive.
No, so we're much closer to what you described first. So we have a very generic simulation environment, but there's some very specific things that are important. Um, One clear example is what are the torque and velocity limits of a motor? You cannot expect it to do something that is not possible on the real robot. So you need to add those limits. And there are a few more things like that, like what kind of delay can you expect between a command? So you need to identify a few of those parameters. And we are actually doing it usually in a what we call a real to sim process. So we take the real robot, really like hang it in the air, we let it shake a little bit, collect data of all the different motors, and then we know which are those important effects that we need to identify. We identify them and add them to the simulator. But simulation speed is the most important thing. So you cannot afford to simulate all those different effects, currents, magnetic fields, etc. You need to abstract all of it away.
That sounded very hard or inexpensive.
And my personal take is that you still need to understand them, even though you're not simulating them.
Mhm. Got it. And so it sounds then that it sounds then like the result of that process is not a general model that you could deploy to any humanoid robot, but one that is specific to the humanoid robot for which you took the real to sim, those key parameters, but that, because you're able to abstract it out to these, some handful of or several handfuls of kind of key parameters, like it's relatively easy um to do new robots.
Yeah, and this was also the surprising part of one of the key learnings of this year is switching robots is fairly easy, as long as the hardware performs reasonably well. So now, as a company, we work with a few different suppliers of robots and a few different partners as well with whom we're working closely. So we've deployed controllers on, let's say, between 5 and 10 different robots. And we see now that making a new robot walk is basically a few days of work. And it should be less. It should be less than 1 day of work if we optimize some of our processes. Now, bringing them to a new task, this is a bit more challenging. This requires more engineering today, and this is what we're focusing on. So one of our key metrics is how much human effort is involved in bringing a new robot to a new task. A new robot is very easy today. A new task is something we're working on.
And in this context, like we've kind of talked a little bit about this, but how specific is a task? Meaning, like, is a task pick and place, or is a task robot in this warehouse picking off of this line and placing into these bins?
And that's a great question. More like pick and place. But there's an interesting concept there, which is we are trying to leverage the information contained in large VLMs to orchestrate and break down complex tasks into clear subtasks. Even though that's not what we're focusing on today, cooking is a great example, a great metaphor. If you wanted to cooking, yes, if you wanted to train the robot to cook every single meal on the planet, and you would say each meal is its own task, you would never finish that, right? Like the set of tasks is huge. But what you could do is you give the recipe to a VLM. You also give it images of what the robot sees. If the recipe says cut a cucumber, the VLM would say, grab the knife, grab the cucumber, and do this sort of motion to cut it. And then you can break it down into much simpler primitives, like cutting things, holding a pan, putting it down somewhere, filling a glass of water, pouring it, things like that. And suddenly the set of these primitives is not infinite anymore. The challenge is that now you need a higher level intelligence that will orchestrate all these primitives. But what's interesting is that part is basically solved with a VLM. It's not 100% there, but it's moving much faster than the actual physical interaction of doing all these motions.
Uh, can you elaborate on that? It's the orchestration is solved, and if so, how is it solved? And what's the relationship between that orchestration and what we talk about as like the reasoning capabilities of these large models? Or is it the same thing or related?
It's similar. So maybe one way to describe this is on our website we have two videos. We have a video of a robot walking in a forest and picking up trash. This is mostly there to showcase what's possible and also play a little bit on our Swiss angle to using our nature. We have another video where the robot is doing the same thing in our office, and in that second video, it's 100% autonomous. So you give it a text prompt. I think we're saying something like, "Pick up the toys in front of you and drop them in the basket at the end." And we're using an off-the-shelf VLM for that. The way this works is we're giving the images to the VLM, and we're allowing it to do tool use to call specific skills of the robot. So the VLM would say, "Oh, I see a toy there on the ground. Let's walk to the toy." And this "let's walk to the toy" is a skill that is actually triggered and executed by the robot. Once we're there, it will trigger "pick up the toy," then go to the basket and drop it off. And so by having a few of those primitives, which are walk to things, I mean, the walking is locomotion, as we discussed, is itself very complicated. So you can walk on stairs, you can walk on a bunch of different complex terrain. But by having like walking, picking things up from the ground, and then dropping them somewhere else, we can recombine it in many, many different ways without any retraining, just by prompting an off the shelf VLM.
When I hear tool use, I hear like separate process or module or model. Um, is that the is that the case? And like, how do you think about, then I think of like if we got a bunch of tools, you've got a bunch of these, separate models or modules. Like, are they actually? Does this architecture imply that they are in fact separate and trained separately, or are they um, more universal somehow?
That's another great question. So in our case specifically today, they are separate, but uh, we are actively working on merging them together into one single model, a more general model. And the hope with that again is that you see some generalization, so you see some interpolation between those different models. The and the way we would do that is actually by still training those different modalities primitives separately, and then using them as data generators to collect a massive amount of data in simulation to then train one of those larger VLAs across the whole data set such that it can perform everything. We're seeing early results of that in our company, so things are going in that direction, but we still need to prove that this actually leads to the generalization we're talking about before.
And hearing you describe that, often when I hear like these kind of student teacher types of approaches, or, I think of like distillation and trying to get to smaller models, you're not necessarily trying to do that. But talk a little bit about the hardware capabilities from a model inference perspective and like where we are in terms of, model size, that kind of thing.
In our plan, if we go through that whole process, we train, let's say, 50 of those primitives, we distill everything. We are still developing a hierarchical pipeline where you have three models interacting with each other. It would start with a relatively large, let's say, VLM that would not be allowed to use reasoning. Um, and the output of that one would be that VLM would go from a very abstract task to clear subtasks, such that if you have a robot here and I tell it go across, like I don't know, go pick something up in the fridge, and would say turn around, go through the door, open the fridge, grab the thing, close the fridge, etc., clear instructions. Then those clear instructions would go to that VLA that we were describing before, where if it receives as instruction open the fridge, it will plan a kinematic motion for the arm to grab the fridge handle and open it just a few seconds into the future. And finally, we have what we call a whole body tracker, which will receive this plan of how the hand should move and how the whole body should move, and then we'll control the motors of that specific robot to execute that motion.
Okay.
Um, Now, the size and frequencies of these models are very different, and that's why we think it makes sense to have three of them. The the final one, the whole body tracker, is a very simple, very small model. Typically, it's a very small transformer. To be completely honest, doesn't even need to be a transformer, but today everything should be a transformer. And that can run very easily at, we typically run them at 50 hertz, 50 times per second, on even on the CPU of the onboard computer of the robot, not even the GPU, because it takes more time to send it to GPU and get it back. Then I'll skip the VLA for now. Going to the VLM, that one is typically fairly hard to run on board on the robot. For now, it's running offboard, either in our office in a server rack or even in the cloud, which creates its own challenges. Once you want to deploy 100 robots in a warehouse, either you have an amazingly good internet connection or you have to install server racks in that warehouse. So we are hoping that robot compute keeps progressing such that we can finally feed those things on the robots themselves, typically on a Jetson. And then the VLA, this is where compute is the most limiting today because we cannot really put it off board. It still needs to run fairly fast, let's say 10 times per second with minimal delay. So it needs to be on board. Um, and they also typically use diffusion, which means that you don't infer it just once. At least part of the network is inferred multiple steps. So this is where compute is the most critical. The onboard compute of the robot is the most critical.
Yeah, I hadn't thought about, in the case of the 1X that we were talking about and these other robots in the home that like they're essentially like their brains are in the cloud. I assume that, somehow we were able to get these models small enough to run locally, which seemed like a lot, but just from a latency perspective, uh that I don't know, it's hard to imagine that being particularly tenable. And consistent as well.
So some of these models, just to clarify, some of these models can fit on the robot. But what we're seeing today is if you want to do some of this more abstract reasoning, so you give it a very abstract task and then it has to orchestrate something for like multiple minutes, there you really benefit from larger models.
Yeah, and I would imagine that, you would want even more abstract models in the home, for consumer tasks than you would require in an industrial setting. Is that true?
Yes, I would say that's true because in an industrial setting, if the task is repetitive, you can more or less pre-compute those very abstract instructions or go from very abstract instructions to clear instructions. In a home, if you have a human just telling you something, then for sure you need this scale of large models.
Are you using off the shelf RL environments or is part of what you're creating, the simulation environment for creating these models?
It is a big step of what we're creating. So we are not building simulators ourselves. We're using existing simulators, including ones from NVIDIA. We also uh, test and experiment with many others. But one of our key know-how is how to properly build those simulation environments, and we have our own custom RL algorithms on top to benefit from that as much as possible.
Got it. So the simulator and the simulation environment are distinct. Is the simulation environment, when you say that, is that the configuration of the environment in the simulator? Like the simulator is like the platform and the simulation environment is like the thing that you create about your scenario? Or is there
Yeah, exactly.
are
Yeah,
there is
that's
there just
exactly it.
those two levels of abstraction or are there three levels of abstraction, I guess is
I guess you would add the RL algorithm as a third component that interacts with both. But that's it. Like the simulator itself is basically a physics engine and a renderer, and then you have to put a robot in there. If you want it to walk on stairs, you have to create stairs. But you cannot just ask the robot to randomly figure out how to walk on very complex stairs. So you have to create a whole what we call a curriculum of difficulty. So you would start with very small stairs and progressively make them harder. And the same is true for all sorts of tasks. If when we're training a robot to open a door, well, we have to create a simulated version of the door. Then we have to help the robots. We have to figure out exactly all these training processes on top of just the scenario itself.
And so as we've talked about this, you've kind of um, positioned RL and imitation as these two alternatives. But is it also possible to use imitation in conjunction with RL to kind of bootstrap learning and like, help the robot get over these, figure out stairs more quickly? Like, is that still a research problem or is that something that, we're able to do in practice now?
That's a good question. It's still a research problem, but we are seeing good signs of life of it. I would say there. I would I can talk about two different ways to combine them. One way is use a few demonstrations to help the RL process, and this is something we're doing very actively. So if you have a human showing like doing the task, you can extract just a little bit of information from that to help the exploration process of the reinforcement learning, such that the robot is not just randomly shaking and trying to figure out everything from scratch, but you're guiding it a little bit towards the right solution. And a completely different way to approach imitation learning plus RL is what we're seeing a bit more um, in other companies and in academia, which is doing more imitation learning for pre-training and then adding some flavor of RL on top to try to improve the behavior after the fact. A big question there is if the imitation learning pre-training was done without any simulator, do you suddenly need to add a simulation again to do the fine tuning or not? And I think this is still a very, very open question.
When I think back to, some of the earliest conversations I had in robotics, like, these are folks like Peter Rabiel. And I remember, I think, this was like pre VLM stuff and maybe even pre Transformer. I don't remember. But like, some of that earliest work was like they'd have hundreds of robots, real robots at Google, like, and they were starting to experiment with RL, I believe, but like it was the robots were RLing and it was very expensive. It used a lot of, you needed to have 100, time on 100 robots. Um, but they didn't have to deal with this RL to sim gap. You're more focused on, simulation and other ways to close that gap, but there are still proponents of, RL in real life. How do you think about like comparing and contrasting those approaches?
There are definitely people who are big proponents of RL in real life, or another way to put it, who are against simulation at all. In some cases, there are good reasons for that, because some things are fundamentally hard to simulate. I can talk about a specific task we're focusing on, which involves the robot manipulating cardboard boxes. So the robot has to walk, pick up the box, bring it somewhere, put it on a table, open it, take what is inside out of the box, and put it on a shelf, for example. Um, in that case, if you break it down into subtasks, most of them are very well simulatable, except one very specific piece of it, which is opening the box. Because you can imagine there is maybe tape on the box. You have to take a knife, cut through the tape to be able to open it. And it's possible, but it's still a lot of effort to simulate the interaction of the tape with the cardboard and exactly how the knife cuts through it. So what we are trying to do there is identify those specific cases where simulation is still limited and use real data, but only for those very specific cases. Well, and then mix it with simulated data of everything else. And we think this is how we basically get the best of both worlds. Or we get as much simulation as possible, and as simulators develop, they'll take more and more of the whole set of tasks. But while there is a gap, we'll use real data for those specific cases.
For the folks that say that, RL in real is better, in what ways would it be better for that particular scenario? Sounds like you would just go through a lot of boxes, but you still like, unless you're giving your robot a utility knife, like, it seems like it's the same problem in real, right?
So I agree with you. I think it is much harder to do it in real life compared to simulation, especially with reinforcement learning. What you could do is do a little bit of imitation learning for that specific case, and that's much easier than letting the robot learn everything from scratch. I would guess the only argument for real life, for pure real life RL, would be that you don't need to deal with simulation, which can be very hard, especially if you don't have expertise in house in terms of how to create those simulated environments and how to tune the simulators to behave nicely. Whereas when everything is in real life, well, you already have the perfect simulator in a way. But on the other hand, you have very expensive hardware, and then any failure and any reset is way more expensive than in simulation.
Yeah, I think it's clear why it's compelling and also why it is aspirational. Like the idea that as humans, we don't simulate the world to learn things. We like explore in the world and we learn that way. And so I'd want my robot to be able uh to do that. Um but we're nowhere near the sample efficiency in robots as we are in humans. So you would end up breaking a lot of robots and or boxes to get there. And then you've only solved one task.
I think another interesting point is that the human reward signal is extremely complicated. If you think like if you're doing some task with your hands, the amount of information you're getting from all the nerves and all your skin, also from your muscles that are tired, etc., is extremely complicated. And we don't have that information at all with a robot. Typically, tactile sensing is very primitive. So if the robot is slowly damaging itself, you wouldn't know until a motor breaks. So if you're doing reinforcement learning in real life, getting rid of behaviors that would damage the motors simply won't work because you'll get, I don't know, maybe one event per week. So the reward is not there. And this is where simulation helps once again, because in simulation we have perfect information about everything. Yeah, we can design reward functions that will avoid, breaking motors, damaging the mechanics of the robot, for example.
And based on your earlier point about incorporating vision, reducing performance or making it more difficult to convert on a model, you know, you one approach to that is, oh, let's just add skin or let's add additional sensors. But all the any additional sensors or each additional sensor rather increases the burden, the computational burden on these models.
Absolutely. Plus, mechanically, it makes everything more brittle. So with cameras, I would say we are there today. We can add cameras to our robots. They're very cheap. They're very reliable. But tactile sensing is just not there today.
And thinking about, crafting that reward function, like, talk a little bit about that process. That is, key in any type of RL is figuring out what that objective function is, a reward function. Um, are is it, how standardized are they for a given task, or do they vary, very widely and require a lot of hand tuning? And maybe as a secondary question on the language side or in like coding agents, there's a lot of talk now about trying to incorporate value functions that allow that provide signal for of positive behavior before the end objective. And I'm curious if value functions are a practical thing in robotics today as well, or a conversation, a research. Are they, is it research or is that something that we're using today?
Absolutely, value functions are part of the RL algorithm itself. So we are training, for example, we mostly using some variant of PPO, which is an actor critic algorithm, which means that you're training both an actor and a critic. The critic is basically a value function. It's not used at deployment. It's only used to help the training of the actor during the training process. And now we're seeing some research into how it could actually be used even at deployment. I think this is more of This is more on the research side. It's not proven yet. And then about reward tuning, it is a big topic. We have 35 people in a company, and quite a few of these people still spend hours tuning rewards. And typically, this is obviously referred to in a negative way. So you don't want people tuning rewards. But I think you have to make a distinction between two types of tuning. There are general rewards that just simply come from the task itself. So if we think again about how a robot is just locomotion, how robots are walking, you would say the task is just go from point A to point B. But in reality, it's a bit more complicated. You want the robot to go from point A to point B. You don't want it to use too much energy to do that. You don't want it to hit the ground too hard. You probably don't want it to slip everywhere. You don't want the arms doing completely crazy motions around it. So by the time you describe it even in text, like what you actually want, you already have, I don't know, maybe 15 lines. And so that translates to 15 different reward functions that you have to come up with and tune. And I think my personal take is that that part of tuning is fine. There is another kind of tuning that tends to happen a lot in RL, which is related to exploration. Is once you've described the perfect task that you want, how do you guide the policy, the training process towards that? For example, if you want a robot that opens a door, you might need to tell it, put your hand close to the handle, then close your fingers, then pull on the door. And these are really things that don't scale across tasks. So, and this is something we're trying to avoid as much as possible. And this is why we're working on other techniques where we can use one or two demonstrations from a human to help the learning process instead of all these manually tuned reward functions.
We're at the end of the year, and this is kind of the natural time for folks to make predictions. Do you have any predictions for the upcoming year or, several years, whatever horizon you'd like to offer in terms of robotics? Like, how do you think about the future?
I said before that I think there isn't a single humanoid robot providing value in the world today. My prediction is that will change around the end of next year, maybe beginning of 2027. So, so we won't. Again, a prediction, hard to predict, hard to say exactly what's going to happen. But I don't think we'll get this, Chat GPT moment where suddenly you have a billion robots everywhere just because you need to build the hardware. It doesn't scale like getting access to Chat GPT, right? But I would predict that around the end of next year, we'll start seeing robots doing actual work. It will be just a few here and there. And then in 2027, 2028, we'll scale both the numbers of robots per task, but also the set of different tasks that these robots can do. Which means that in the coming years, we'll go from, I don't know, hundreds of robots to thousands, and then very quickly to millions, tens of millions, etc.
And presumably, you see that happening first in industrial settings, and then consumer.
This is my prediction, yes. That we'll see that first in industrial, then consumer, so at home. And I hope that after that, we can go to crazier applications. Like we should really send humanoid robots to Mars to build colonies before humans land there.
When you think about the currently available robots that you have, seen and or worked with, like what are they all kind of the same? Like, are all the dogs the same? All the humanoids are roughly the same, or do you see, big differences between them from a hardware perspective? And if so, like, are there, ones that are particularly exciting for you now?
It's a great question. There are probably three or four different strategies you can take in terms of how you're designing your humanoid robot. Specifically, what kind of actuators you use, what kind of gearboxes. And since there are many companies exploring that space, everything is happening in parallel. The, no matter which of those strategies you take, there are a few companies in the US, maybe one in Europe, and probably 50 in China building that exact thing. So the competition is really fierce. One part where hardware is not there yet today is on the end effectors, on the hands. It's still debatable if you actually need very dexterous hands. I think one of the big reasons why many companies develop hands with high dexterity, so like more than 20 degrees of freedom in a hand, is because they're using imitation learning. They're imitating humans, which means that you need to be able to imitate everything a human does. Once you go the RL route, you can learn other kinds of behaviors with much simpler grippers. But the debate is still open on that.
Again, we've been talking about, dogs and humanoids. Um, but there's this broader question, which is humanoid the best form factor for a robot? Like, should we be making robots with two arms, two legs? Do you think that that's the way to go? Or is are we kind of anchored on this because it's our form, but there are, better forms that you've seen or think about?
It's another great question. So I worked on more than 25 robots, I think, by now. So any number of legs and arms you can imagine, from 0 to probably 4, 5, 6 legs. And there is room for all sorts of robots in the world. Honestly, I mostly use, and as a company, we use the word humanoid for the lack of a better word. What we mean by that is not the human form factor, but human capabilities. So very basically, we want robots that can go where humans go and can manipulate their environments in a similar way to how humans do that. So probably you would need at least two arms with some sort of end effector to interact with the environment. And then whether you have legs or wheels, and both are fine. Both have their own applications. So you can go a long way, especially in industry with a wheeled platform. And we're working with robots like that as well. Having said that, it's surprising how quickly wheeled platforms get stuck. A very common thing that easy to imagine is if the floor is not perfectly flat, if you have something, you have cables or of course stairs, your wheel platform is stuck. But another very important part is also the footprint. So with those wheeled platforms, you have two choices. Either you make them very large, and then they're stable by default because they have a very large footprint, but they don't fit through tight spaces anymore. And very quickly, especially in slightly older industrial settings, you have tight spaces.
And the alternative is maybe some gyroscopic Segway-like thing?
That could be one. Typically what we see is that you just have a small platform, which
Uh-huh.
means that you have to be very, very careful how you move the torso on top, because if you
Okay.
lean too far, it just falls over. I haven't seen the gyroscopic platform yet.
Okay.
I still think a three-legged robot is probably the coolest robot I've seen so far, but it's maybe not the most applicable for industrial tasks on Earth.
And then, maybe one more question. There are, quite a few now, like robotics kits or, robots are getting more accessible for folks that are interested in the space and want to play, but, don't have access to a humanoid robot, like, or don't have any robots. Like, what are some cool things that someone can, order now, maybe get by the holidays or soon thereafter, meaning not like pre-order for 2027 and start playing around. Like if you were, advising someone who is like excited about getting their hands dirty, like, what would you tell them to start doing?
There's an amazing community around Hugging Face and their little robot project, where they have very cheap robot arms, and they can help you learn about the whole um, teleoperation, data collection, training, and deployment pipeline with those arms. So that's a really good way to learn about that. For the more like locomotion and reinforcement learning aspect, it's a little bit harder because you probably want a robot with legs. Which also means that the robot should be able to fall and stand up without completely breaking. I think the best bet there is the Chinese quadrupeds that are really getting fairly cheap. It's still multiple thousands of dollars, but let's say it's affordable for a university or a school, or if you really want to go much deeper into that at home as well.
And, you get your quadruped, um, and you unbox it. Like, what can you do with it? Or where do you start with, trying to do some experiments with it?
So when you unbox it, it can typically can already do quite a lot. So it will be able to walk. In some cases, they even have things like SLAM pipelines, so it can do some navigation, can avoid obstacles, things like that. But then the challenge is that you want to get rid of all that software and basically recreate it from scratch. And there are many communities online, there are many GitHub repos that help you get started. The unit we go to is probably the most standard platform, so I would start there. And there are people, and there are people who open source already everything from training to deploying code, deploying these policies on those robots.
Okay, cool, awesome. Well, Nikita, thanks so much for jumping on and sharing a bit about what you're up to. Very cool stuff.
Thank you so much. Really enjoyed this.
Thank you.